Hi, we are Team Vicharaka from the Indian Institute of Science, Bengaluru. We are a group of first and second year students passionate about robotics and space exploration. Now presenting before you VICHARAK, our first generation Mars rover, designed and built entirely by us. Now let us take you behind the build, starting with the people who made it possible.
Our team is structured to ensure smooth coordination and efficient task execution. At the top, we have a team leader overseeing the overall direction and progress. Supporting him is the technical lead who provides technical guidance and advice, and the management lead who handles planning, communication, and logistics. To streamline our efforts, we divided the work into 5 specialized subgroups: mechanical, electronics, robotic arm, science, and software. Each group focuses on a specific domain, allowing us to tackle complex challenges efficiently. Now let us go into the details of each subgroup. The mechanical team is responsible for structural design, modeling components on CAD software, carrying out fabrication, and performing finite element analysis to ensure structural reliability. The electronics team is tasked with designing custom PCBs, performing soldering, and integrating the power system and sensors. The science team is responsible for conducting environmental analysis, studying terrain and soil properties, and developing a deep sampling mechanism for biosample collection. The robotic arm team is assigned to design and build a highly stable manipulator capable of precise maneuvers to perform the intended tasks effectively. Lastly, the software team is focused on running system-level simulations, implementing control algorithms, and developing the autonomy stack for seamless coordination between hardware and logic.
As first-time participants and a small growing team, we saw European Rover Challenge as more than just a competition. It's a chance to test our skills, learn from others, and grow through hands-on experience. We are building everything from the ground up and learning every day. Excited to be a part of global space robotics community.
Our mechanical system features a robust 6-wheel differential rocker bogie suspension engineered for superior mobility across challenging terrains. The chassis is constructed from aerospace grade 6061 aluminum fabricated using laser cutting, welding and precision machining. Designed for rapid assembly and disassembly with a compact yet stable wheelbase of 93 cm by 84 cm. The system can effortlessly traverse rugged landscapes, tackle steep inclines of up to 50 degree and descend near vertical drops with stability. The wheels are specially designed for maximum traction across diverse terrains.
In an emergency, a physical stop switch cuts power to all subsystems except the main computer and the communication module.
Our rover's electronic subsystem is designed with a robust and modular architecture to control and power efficiently all the electronic subsystems present in the rover. The main power distribution board is a custom-made hand-soldered one that integrates individual motor current measurement and fail-safe system to enhance system's reliability. Powering the main power distribution board is a STM32 microcontroller that also includes undervoltage, overcurrent and thermal failsafe mechanisms. The rover is powered by a 21 amp hour 24 volt lithium ion battery, providing over 180 minutes of runtime with all subsystems operating simultaneously. All electronic boards are modular and easily swappable, allowing for quick replacement in case of any failures. The TNZ 4.1 microcontroller handles the lower level tasks and communicates with the main power distribution board via UART, enabling supervisory control of the power distribution system from the base station. The motor control system is implemented as a closed loop PID system, ensuring precise rotational speed and torque control for each wheel.
Our rover is built for autonomous navigation in places where GPS doesn't work. It uses a depth camera and a 10-axis IMU to perform visual inertial odometry. The depth camera also provides the rover with the 3D data, which it uses to make 3D maps and detect obstacles. An extended carbon filter combines the data from the IMU, depth camera and the wheel sensors to improve the accuracy over time.
For finding targets, the rover uses image processing to detect Aruko markers and objects. When it sees a target, it plans the best path to reach it while avoiding obstacles. All of this runs on ROS2, which connects all software parts and keeps everything running smoothly. For communication, we use a high-speed 5G link for real-time video and control. If 5G fails, a long-range ubiquitous system takes over. And for manual control or emergencies, we use Kite as backup.
Our drone features a hybrid combination of pusher and tractor mechanism, giving a flight time around 15 minutes and weighs under 1.5 kg. Our setup consists of 935 kV brushless motors, 50 ampere 4-in-1 ESC and Pixoc light controller. Tractor pusher mechanism enhances aerodynamic efficiency, cooling and stability. Tractor props at the front operate the undisturbed air, offering high thrust efficiency. Pusher props at the rear help to create a balanced thrust vector that reduces turbulence around the central fuselage. For altitude measurement, we employ a 1D LiDAR sensor, enabling precise control during takeoff, landing, and low altitude hovering. A depth camera, in combination with an onboard Raspberry Pi 5, handles the autonomous tasks. Our drone is capable of executing agile maneuvers including forward, backward, lateral, and hover movements. Even under windy conditions, it features a controlled takeoff and landing sequence, with optimized ascent and descent speeds tailored for operation over rough terrain.
In the event of an abrupt power loss, the drone activates an emergency stop mechanism. It first initiates a slow stabilized descent while countering wind drift, then hovers approximately 30 cm above the ground, using the downwash from the propellers to clear the landing area. Once the area is deemed safe, it gently drops onto its landing legs, completing a secure and efficient emergency landing.
This is the Bioscience team, and we have been developing a 4-part system for our rover so that it can take any scientific exploration challenge headfirst. For the exploration subtask, we have developed a testing module which utilizes samples collected using the manipulator.
The collected sample is then tested using 3 different chemical assays. The first is Bradford's assay, which is used for testing proteins, and the color changes from brown to blue. The second is Sudan 3 test for lipids, and the color changes to red. The third is the litmus test, and the color changes to blue, showing the presence of ammonium salt.
We have designed a composite drill mechanism combining aspects from both auger and core style of drills. The cylindrical compartment stores the sample and is then sealed by the auger face and the flag. To prepare for the scientific exploration subtask, we have been studying research papers and using softwares such as JMARS.
For our first generation of robotic arm, we decided to go with a 6-degree of configuration model to provide for flexibility and harmonic drives to provide for strength and precise control, and also combinedly with closed loop stepper motors, which altogether gives us a precise and capable arm.
The arm structure is built from aluminum 6061, chosen for its excellent balance of strength and weight. We extensively used finite element analysis during the design process to optimize the mechanical structure and achieve the best possible weight to strength ratio.
Each motor of our robotic arm is controlled via closed-loop drivers using RS485 communication, ensuring robust and reliable system performance. With carefully tuned PID parameters, each joint moves smoothly and quietly even while handling payloads of up to 7 kilograms without strain. For manual control, we developed a custom-designed graphical user interface that enables real-time servoing of the arm using keyboard inputs. Additionally, we integrated a FlySky transmitter system as an alternative control method, providing dual redundancy for enhanced reliability. This setup offers intuitive and responsive control, allowing seamless execution of complex tasks such as lifting, rotating, and switching.
Here at ISC, our club is dedicated to innovation and hands-on experience. Thanks to our sponsors RBCCPS and Art Park, we were able to organize a drone workshop in which members could design, build and fly their own drones, which provided them with valuable technical expertise. And on the occasion of ISC's Open Day, we were able to present our Mars Rover project, which was able to attract people from all backgrounds.